really fast-moving lava, 30, 40, even more miles per hour.
Iko natembea na hotere ya kabambi sana, viro 3 metre ya hotere.
I've just come over the edge. If any of this rock goes here, that's it for both of us.
Rock!
As you get to the top of the volcano and peer into this huge hole which has walls of a few hundred meters high and over 1 kilometer in diameter, it's like looking almost into the gateway to hell, because at the bottom of that hole is the world's largest lava lake, so a few hundred meters in diameter itself. It's a giant orange lake of magma. There is a kind of majesty and an alluring magic to the lava lake because it is so bright, it's so orange, and it's so dynamic. It's churning like a cauldron. It's just bubbling and whirling, almost like water, but water which is 800 degrees Celsius.
I can feel my heart rate going up just putting the harness on.
Wait till you look over the edge.
Yeah.
Last bit before we go down, kicking rocks off. If you do kick a rock off, big shout,
Rock!
okay. One of these rocks hits someone on the head, it'll kill them, even with these helmets on.
Okay.
Blend of excitement and nerves, I'll be honest with you, yeah.
You should enjoy the view first before we go over, because after that you're going to be fairly busy.
All the while, as the wind swirls within the cauldron, it's bringing off bits of loose rock which tumble down the sides right around your head as you're desperately clinging onto a very thin rope.
Ooh.
As a geologist, probably one of your dreams is to go into a volcano. But with that comes a significant amount of risk, because it's a long way down and you're going into a very hostile environment.
Try not to do that, because there are sections, if you do that, that the whole slope will go.
Yeah.
All of this is just waiting to fall.
Well, from a scientific point of view, it's critical, because some of the instrumentation that you want to put on the volcano needs to be as close to the lava lake as possible. So although it looks incredibly risky, that risk is for a reason.
Chris is down.
Thanks, Dad. Don't look back.
So getting down to tier 2 at the end of the abseil was just a huge relief. We could then start the science. So there are a number of different ways of trying to understand the behaviour of volcanoes, and also when volcanoes may erupt. And that's because the volcanoes give off a number of different signals. So on our expedition, Kayla, who's a geochemist and a petrologist, somebody who looks at rocks, her objective was to actually look at the gases coming out of the volcano, in particular carbon dioxide and sulfur dioxide.
The real power in gas measurements is that it can tell us about the entire system miles and miles beneath your feet. So that's where the action is. That is the driving force of volcanism. It's controlled deep down in the guts of the volcano.
It's really important to know what the levels of those gases are in normal times, and then what levels those gases get up to when the volcano is moving towards an eruption and during eruption.
If we see all of a sudden a huge spike in the amount of sulfur dioxide that's coming out of the crater, that could be something that happens before an eruption.
We're not just concerned with when the volcano is going to erupt, we're also concerned with what will come out of the volcano. Because if we have very, very runny lavas, and these are lavas which are typically quite low in silica, and so those lavas will be able to go from the volcano to the populated areas much more quickly, giving us less time to warn the local populations and for them to evacuate. So one way to try and assess the viscosity or the runniness of lava is actually to go and get samples of lava.
Let me show you one of the samples that I collected from the active vent. We can see that this sample is a glassy black matrix. We can see a lot of bubbles here around and a few tiny white crystals. We know that the composition of this volcano are low in silica, very low, below 40%, and this makes these lava very fluid, so they have low viscosity. They will be flowing like water along the flanks of the volcano, so I suspect that if there is a new eruption with this composition, it might be flowing even faster than during 2002.
That is a clear indication that we need as best possible a warning system to give people chance to remove themselves out of harm's way.
This is a custom-built microphone, and it's capable of recording sounds beyond the threshold of human hearing.
So Jeff is a geophysicist, and he has this rather unusual interest in the voice of volcanoes.
Volcanoes speak at low frequencies. They generate sounds that we can hear, but they also generate this world of infrasound that we want to recognize and understand, so that when that tone changes in the future, we will be able to understand what's going on.
As the lava lake level goes up and down, it moves the entire air mass within the crater itself. And the volcano, in essence, is acting like a giant trombone. There's air going up and down within there, and that kind of motion of the air produces a noise which can be heard with infrasound.
The infrasound is detecting motions that occur both at the lava lake surface and also inside this bowl that can be vibrating. You don't think of a caldera this big as being an air mass that may be going up and down.
No.
But that's what we have discovered. The crater actually acts as a musical instrument. So we can't hear infrasound, but we can speed it up and we can make it audible. Here's an example of the infrasound being sped up by a factor of 40. This to me is exciting. I see the data, it's good quality, and I am happy. I do believe that infrasound is a fundamental tool for volcano monitoring, and not too far down the road, we will be able to use infrasound monitoring here to better forecast Nyiragongo's next eruption.
But we want to develop techniques which allow us to monitor the volcano cheaply, but also safely. So anything we can pull data from digitally and look at in another location, maybe on the other side of the planet, is good news. But despite that, it is clear that that volcano needs to be monitored more closely with all of the cutting edge tools we have because of the people living around us. And that has value not just for understanding the behavior of Nyiragongo, but the tools and technologies and the science we develop at Nyiragongo can potentially be applied to volcanoes elsewhere on Earth.